versus independent. When something is independent, it means that outcome has no effect on anything else. Just like an independent person. They have nothing to do with anybody else. A dependent person depends on something else happening, depends on someone else. And a dependent probability depends on something else's outcome. So we look at two things. Most of the time, if it's independent, like if I toss a coin and then I roll a die, does tossing my coin have any effect on rolling my die? Those are two completely independent events. The second one is independent of the first one. A dependent event would be I pull a king, I keep it in my hand, no replacement, and now I go to pull another king. This is a totally dependent case because if I don't replace this and I'm holding this king, now there's not 4 kings in my deck. How many are there? 3. And now there's not 52 cards in my deck. There are 51 cards in my deck. So where my probability of 4 out of 52 would be here, it's 3 out of 51. This probability will change because something made it change. If it's dependent on something else, it will change. If I take that king, if I pull a king, and I replace it, I'm still a 4 out of 52, and if I pull another king, this is still a 4 out of 52, because I put it back. So that is independent. Doesn't matter what I pull again. All of them are back to where I started from. So dependency has a big thing with this. And pretty soon we'll talk mutually exclusive and exclusive. But for this little part, we're going to talk dependency. Okay. And conditional probability, you can almost feel it in the words. Conditional probability depends on something else. There's a condition to be met. It depends on something else happening. So I gave you the notes for today. And just feel free to write on them, embellish them, put your examples on them, whatever you need to do with them. Conditional probability is the probability of an event occurring given that another event has already occurred. The probability of event B occurring given event A has already happened is written like this. This is the given line. This is tricky. And we read it like this. The probability of B occurring given A has occurred. So, which one is dependent, B or A? B is dependent on A. A is independent. A does whatever A wants to. B says, well, A did this, now that's going to affect me. B happens given A. A says, do whatever you need to do. I'll do it. B says, well, let me see what happens in A. So this is very, very important that we remember this. For example, 2 cards, and cards work great with this because why? We can replace cards. On a spinner, on tossing a coin, rolling a die, there's nothing to replace. Those are going to be independent. But a deck of cards that you hold in your hand, you can either replace that card and pull another one, or you can leave it out. So 2 cards are selected in sequence from a deck. Find the probability that the second is a queen. I want a queen given the first is a king. And assume the king is not replaced. You have to know how to write out your probabilities. So this says the probability that a queen is drawn given that a king was drawn. So we have 2 things that happened. The king was drawn, then the queen was drawn. So first time through, what is the probability of drawing a king from a deck of cards? 4 out of 52. I have 4 kings. I have 52 cards. Now, I do not replace this. I hold this in my hand. How many cards are left to choose from? 51. And of those, how many of them are queens? 4. So what am I going to do with these guys? Let's multiply. Generally, when they sit like this inside of parentheses, I'm going to multiply. I'm going to multiply the tops, and I'm going to multiply the bottoms. I think this is 2, 6, 5, 8. I did it in my head.
Wow.
No, I didn't do it in my head. I'm doing this over the years. I know that 52 is but I said I haven't done this in a year since last year, so let me just check that in the book. Thank you. It reduces down. It would be 16 on top. Look at that. I forgot to multiply the top ones. I multiplied the hard ones and didn't multiply the top ones. And so now, this is conditional. If this was not conditional, how could I change this? How could I change this to be independent? How could I change this scenario to make these 2 independent events? Put the cards back. If I replace it, then I have 2 independent events. Because pulling a queen has no effect on what was done with the king. Because the king was put back into the deck. So see the difference between an independent and a dependent event? Okay? Alright. So you let's see what else we have here. The charts are the trickiest ones, but I love the charts. Okay. Work with me on this. Don't write in your book, but you might want to write this down on your note page because these are very, very tricky. I should have actually given you a sheet like this. So if you just kind of draw this for me. Give you a minute. Just kind of copy this into your notebooks. Because once you get the hang of the chart, you'll be fine. Can you see it okay? These totals will add down this way, and they add across this way. And both row and column total to this total number. 102 is the total between these 2 and these 2. So we're checking to see if the child has a high IQ and if their gene is present or not for this IQ, for this particular IQ thing. Now, here's the thing with the given. Find the probability that a child who has a high IQ given the child has the gene. Now, the given part is what comes first, right? That's the independent part. I got to know first if I have the gene. So when we come to here, what we do is we look for the gene. We look for the gene to be present, and we circle it. Now when we do the dependent part, it's got to come from that circle because it's dependent on that column only. So what is the probability that the child has a high IQ? 33, stay in this little circle, out of 72. Okay, the given part is the part we do first. That's the independent part. Then the dependent part is what we look at next, inside of the given. When they give us a table, circle what the given wants done. Okay. And you can reduce this down to given the gene present. That's the bottom one. That's this guy right down here. I added more than they had because I wanted to do a few more things. It comes down to 0.458. Now, continue reading the chart with me. What is the probability that the gene is present? I'm only asking you one thing. So it has to be independent because nothing else depends on this. 72 out of 102. Very good. Here's my gene present. I have 72 people that had the gene present, and this is a total. Go off your grand total. Good, Tori. Go right off your grand total. So this reduces down 3 decimal places. What is the probability that the person has a normal IQ? I go just to my normal IQ. And I say, okay, just my normal IQ. How many people had a normal IQ? 50 out of what? 102. And this reduces down to 0.490. Find the probability that the person had a normal IQ given that the gene is not present. This has a normal IQ given no gene. This is the guy I got to look at first. So I go to the gene not present. And I can only look in this part. This part is dependent on this. So what'd you say, Chris? 11 is my normal out of 30. Stay right in that circle. Don't leave it because that's the dependency. So 11 out of 30 gives me 0.367. See how to read this chart? This chart, I love these charts for dependencies because we can see this one right here, probability that the gene is present, is independent event. It's one single event. So I look, gene present, there's 72 that had a gene present. I don't care what their IQs were. I just care that their gene was present. Their gene present over the total. Normal IQ, I just care that they had a normal IQ over this one. Then when I do my given, I can only stay in that little section because that's the dependency. Make sense? What does it make sense to you? So if you look at the next one, try it once. Let's stay right on this chart. Find the probability that the child does not have the gene. The probability that the child does not have the gene. What would you say? 30 out of 102. Is that a dependent event or an independent event? Independent. I'm only asking one thing. It depends on nothing else. So I say gene present, gene not present. How many? 30. What's my bottom number? 102. 30 out of 102, and it reduces down to 0.294. Part B says find the probability that the child does not have the gene given the child has a normal IQ. No gene, given, normal IQ. So where do I go first? Which part of that is the independent part? Normal IQ. Good, because that's what's going to come first. If something comes first, does anything else influence that? You're the pioneer. You come first. You do it. What your results are will influence what happens next. So the normal IQ. I look for my normal IQ. I'm in this piece. I can't leave. Where's no gene? 11 out of 50. And again, I bring it down to 3 decimals, 0.22. The fractions are nice to see the part over whole. I like to see that there. But if you're going to compare decimals, it's probably easier. This has the probability that the gene not present. Did we do a gene not present only? No gene. This is like almost 30%, about 29%, not 70%. So if you look at it in terms of percentages, more people have the gene present than don't have it present. If you say 72 out of 102, and you say 30 out of 102, they have the same denominator. Yeah, that makes sense to me. That 70 has a lot more than 30. But sometimes comparing decimals are just a little bit easier to see, especially if you reduce your fractions. If you reduce your fractions and they don't have the same denominator, then you have to convert them all over again. Do we kind of feel this a little bit? See what a dependency is versus an independent? Everybody okay with the chart? Always go to the given. Once you have a given, that's where you have to stay. Whether it's a column or a row, you can't leave that. Okay. So we did those. So 2 events are independent. Now watch how they word this. 2 events are independent if the occurrence of one event does not affect the probability of the other, such as replacing those cards. If I replace those cards, I'm back to where I started from. It didn't affect what I'm about to do next. So they write it like this, that the probability of B, let me just write this out. The probability of B, given A has occurred, is still going to just be the probability of B, because A had no effect on it. Such as pulling a king after you pulled a queen. If I replace that queen, pulling a king is still 4 out of 52, which would normally be my pulling a king, right? So we rewrite it like this. Or if we reverse this, the probability of A given that B occurred, if B has no bearing on A, then A is simply the probability of A, which probably is a little confusing until you think about words in this. 2 events are dependent if the occurrence of one does have an effect on the other. Then we cannot say this statement, because then when I say this statement, it is not equal to the probability of B. We had an effect on B. So let's take case in point. Event A is drawing a queen. Event B is drawing a king. Stay with me to work this out. I need you to understand this, because just looking at these little letters up there is confusing. So now, if this is independent, if it's independent, I have to replace this. It's with replacement. So I'm saying this. The probability of B getting a king, given that I drew a queen. If I drew a queen and I put it back, what is the probability of drawing a king? 4 out of 52. So isn't the probability of me drawing a king by itself 4 out of 52? So don't these match? That's what this is saying. This is independent. It is exactly B, what it normally would be. Here's the reverse. This is no replacement. So I'm going to draw my king after I drew my queen. So if I draw my queen and I do not replace it, I'm holding it in my hand, what is now the probability of drawing a king? 4 out of 51. But drawing a king by itself is 4 out of 52. So therefore, they are not the same. You have a dependency, it's going to change. It's not the same. That's what all these A/B things mean. It's confusing when they say A and B and then they reverse it B and A. We think something has changed there. It's just a different way that they worded it. But in essence, it means if you do something to change that result, it can't be the normal probability. It can't be the normal probability of pulling a card out of the deck. Marbles in a jar is another one with replacement. Those are always popular too. Maybe that's a little easier to see. If I have 3 red marbles and 2 blue marbles, altogether I have 5 marbles in my jar. 3 reds, 2 blues. If I pull out a marble and I replace it, if I replace, what is the probability of getting a red? 3 out of 5. What is the probability of getting a blue? All the time, right? All the time that's going to stay the same because I'm putting the marble back. Now, watch. If I do not replace, if I pull a red, what is the probability of a red? What is the probability of a blue? Oh, 2 out of 4. That changed, didn't it? Because that's the guy I did last. He depended on what happened first. Because I pulled it and I kept it in my hand. I could reverse it too. I could say, first time through, I pull a blue. 2 out of 5. I keep it in my hand. Then I pull a red. 3 out of 4. It's changing. So if something changes that probability, it's because it was dependent on what happened first. It's a dependent event. Do we feel that? This is tricky. This is the tricky part. I want you all to wake up, slap yourselves in the face a little bit. Let's move on. Coffee. I could go for that too. Decide whether the events are independent or dependent. I select a king from a deck. That's A. I don't replace it. Then I select a queen from the same deck. Dependent on the first one, right? Who is the first one?
A.
Drawing a king. So this part is always independent. The first guy has no effect if nothing else affected it, right? But the second guy is my dependent event. The first one is always going to be independent. It is the second guy that tells me if this whole thing is dependent or not. Okay? Tossing a coin and getting a heads, A, and then rolling a 6-sided dice and getting a 6. Dependent? Independent. Independent because does one have any effect on the other? No. I can't hold that coin, I can't take it away, it doesn't affect my roll of my dice, or vice versa. If I rolled my dice first and then I flip the coin, still independent. It's not going to change my results. Okay, you take a minute and think about these guys. Oops, I just did something weird. I don't know. So once in a while I did something weird. Okay, back to normal. Okay, you guys think about this. Think about these. So smoking a pack of cigarettes per day, that's A. And developing emphysema, a chronic lung disease, that's B. So I want to know the probability of B given A. Given that you smoke a pack a day, will you develop lung disease? Is that dependent or independent? Dependent. The is kind of like your subjective probability. Can I really put a number on this? Does it always have to happen? Never have to happen? This is kind of a subjective thing, more like a common sense thing. If I study, I'll do better on the test. If I don't study, I still may do better on the test because I know my information real well, but chances are I won't do as well. So this is kind of like a subjective thing. But this has my effect on this. Cause and effect. The cause is I'm smoking a pack of cigarettes every day. My effect is I will get lung cancer. That's dependent. Tossing a coin and getting a head, and then tossing the coin again and getting a tails. Getting my tails given that I already had a head. Is that a dependent or an independent event? Independent. Why? Because it has no effect on the other toss, right? Each toss doesn't matter what I tossed before. I could toss 25 heads in a row. I still have the same probability of getting a head, one out of two. Are we feeling those? I got very squeaky shoes on. Okay, so we kind of see what's going on here, and we've been doing them together because I like to use examples rather than just use A's and B's because it makes no sense with A's and B's. So we've noticed that we've been multiplying these. And for dependent events, all it's saying is when you multiply the first one, just remember to take out what's changed. When I'm independent, I multiply them the same, that nothing caused them to change. This is the fact that we took out the king, 4 out of 52. This is the fact that we removed a card and took out a queen, 4 out of 51. This is when we replaced it, 4 out of 52, 4 out of 52. Just a replace, a no replace. Pulling the marbles out of your deck. So we're just going to use the multiplication rule. This is your multiplication rule when you do these. And since you put the probabilities like in parentheses, usually when you put two things in parentheses like that, you multiply them. So two cards are selected without replacing. If I do not replace, am I dependent or independent? If I do not replace, I am dependent. Because doesn't it depend what I'm holding in my hand? What happens next? If I pull out a king and I hold it in my hand, how many cards are left? 51. And how many kings are left? 3 left. So you're not going to get a 4 out of 52 chance again of pulling a king. Find the probability of selecting a king and then selecting a queen. So I want a queen given that I got my king first. So my probability of getting a queen after I got a king. What is my probability of getting a king? 4 out of 52. Then I'm going to hold it in my hand. And what is my probability of getting a queen? 4 out of 51. So we did multiply these before. Even though I multiplied it incorrectly. We did multiply these before. Kind of think of it when they do this, and you can write it like this. The probability of getting a queen and a king and a queen. And you got to tell them it's with replacement or without replacement. Okay, without replacing it. And reduce this down, rather than reduce it to a reduced fraction, I like to reduce it down to decimals. You could see how you could obviously see that's really small, but this is even smaller. If you move this, it's less than 1% chance that this is going to happen. If you play cards, these are the probabilities to look at. Okay. A coin is tossed and a die is rolled. If I toss a coin and I roll a die, dependent or independent? Independent. I need to know this first. So I want find the probability of getting a heads and a 6. So what is the probability of tossing it and getting a head? 1 out of 2. What is the probability of getting a 6? 1 out of 6, and we multiply. Do these look like your trees that we used to multiply the branches? Remember I put them on your branches? This is your multiplication rule. So when we did your heads versus tails, here, Miss Minnie, and then I did 1, 2, 3, 4, 5, 6. I said this was 1/2, this is 1/6, and we got 1/12. There's where our multiplication rule came in. I like to start with it on the tree because I think it makes more sense. 1/2 times 1/6, and then when we do this, this totally makes sense to us, or it should make sense to us. Okay. Here's a tricky one. Find the probability that a salmon swims successfully through a dam is 0.85. Find the probability that 2 salmon are successful through that dam. First of all, does one swimming through have any effect on another one swimming through? Same as if you swam through. Does it affect when you swim through that dam if your friend swims behind you and gets through that dam? No. These are independent events. So is this going to change? No. So the first salmon going through is 0.85. 85 out of 100. The second salmon going through is still 0.85. And can't probabilities be decimals? So we multiply them, and we get, we don't have that one. 0.723. Okay, so the probability that the two of them come through is 0.723. The reason that it doesn't say 0.85 is because your chances change a little bit with expecting 2 to be successful. 2 cards are selected from a standard deck without replacement. So does this make me independent or dependent? Dependent. Tori, agree? Dependent? Okay. I couldn't read what you were saying. I tried to look at your mouth. I couldn't read your mouth that one. Because usually you mouth the words and I could see it. Some of you are afraid to say it out loud, or either that or I can't hear it from up here. Find the probability that they are both hearts. I want a heart, and then I want another heart. And I am going to not replace that. I'm going to hold that in my hand. So the first heart is what? How many hearts in your deck? What did you tell me? I'm sorry. No, what did you say the first time? 1 out of 1 out of 10? 13 out of 52. Now you could have said, I thought you said 1 out of 4. Because 1 out of 4 is there's 4 suits. However, that makes it hard to subtract 1 from it. So I wanted to keep the 52. That's why I asked you again. So now, I am not replacing it. I'm going to hold it in my hand. How many cards now do I have to choose from? 51. How many hearts are left? 12. And now I multiply. And this one, I don't know what it comes down to, but it comes out to be 0.059. Are we kind of feeling this? Yeah? The multiplication rule? Not bad. It's not bad. The key part to the multiplication rule is, am I replacing it or am I not replacing it? We're almost done. This one, let's hit the 4, and then on Monday we hit 5. My goal is to kind of be done with 3.2 on Monday. This way I can give you a little quiz on Tuesday, and then you have a break and we kind of took it at a good break. Okay. Now, this is where, in the old book, they never did these, but I guess these surgeries have become so popular, they threw these surgeries in. For ACL reconstructive surgery, the probability that surgery is successful is 0.95. Find the probability that 3 ACL surgeries are successful, 3 in a row, like not on the same person. Is this an independent or dependent event? Independent. One has nothing to do with the other one, right? I'm hoping the doctor can be successful on each one of these. So we say successful surgery 1, 2, 3. We put in the 0.95. And what do we do with these 0.95s? We multiply them. If you added them all up, they'd be greater than 1. Could I have a probability greater than 1? No. So therefore, make sure you multiply them. When I multiply them, I get 0.857. Okay? Another little hint, if they give you a decimal, it's probably got to be independent, because how do you change that decimal? How do you reduce that decimal now? It's almost impossible. So know that that'll probably always be independent for our sake. Find the probability that none of these surgeries is successful. So here's your problem of a case. If the probability of success is 0.95, yeah, the probability that it's not successful is 1 minus this, 0.05. It's not 0.5, it's 0.05. There's a 5% chance that when I do the surgery, it's not going to be successful. Find that none of the 3 surgeries are successful, not successful, not successful, not successful. What do I do? 0.05 times 0.05, good. 0.05 to the third. And that gives us a small number, 0.000125. It is far less than 0.01% that the 3 that I do is not successful. So that's also good to consider when you're selecting a doctor for these surgeries. Okay? Now, here's your complement case. I want you to pay attention to this one. Find the probability that at least one of the 3 will be successful. So what cannot happen? One of the 3. I can have my first one successful and then not. I can have my second one successful. I can have my third one successful. What is the only thing I can't have? Well, no, I can have 2 successful. Yeah. I can't just have, I can have 1. I can have 2 successful. All 3 of them can't be what? All 3 of them can't be not successful. All 3 of them cannot be not. I always have to have an S in here. I'm going to keep on going, but I'll be here a very long time. The only one that I can't have is all 3 non-successful. So if I have to keep doing all of these, it's going to take me a long time to multiply all those things together once I figure them out, right? So instead, I'll do 1 minus my 0.00125. This is my 3 didn't work. That's the only thing I can't have in this. So when I subtract this out, I get this. This is your complement case. This is one of the times you would really, really want to use this complement case. See it? I would first have to figure out all the other possibilities, and then I'd have to multiply them all out, and then I'd have to add them all together. So it'll take me a very long time. So instead, I use my complement case. The only thing I can't have is all bad ones. Make sense? Okay. All right. I guess we'll close it up. Monday we'll do 5, and then we'll do some class.